I'm Dr. Jamie Blanche, and I am a postdoctoral research associate at the University of Glasgow. My key research area is in sensing, non-contact sensing, and the integration of that data with cyber-physical systems. And to give an overview of the paper as it's been published, so we have focused on porous reservoir-grade sandstones, and we basically applied it 3 separate experiments. So static fluid presence, dynamic load, and dynamic fluid ingress. Now, in each of these experiments, we were successful in detecting a contrast using the radar. So the motivation for this work has really been about embedded sensing and getting embedded sensors into reservoir-grade porous rocks. Historically, that's been for understanding how hydrocarbon reservoirs are behaving ideally in real time. But more recently, this has actually been about incorporating sustainability and how, for example, carbon capture could be stored in subsurface reservoirs as well. So one of the advantages of FMCW radar that we've seen in our results is that it can differentiate between fluids such as deionized water and kerosene. It can also differentiate between a sample that's dry, a sample that's partially saturated with these materials. It's also sensitive to the presence of metals. So anything with a high relative permittivity is going to give you a strong response, and the radar can be used as an indicator of that as well. The detection of imminent failure by up to 15 seconds, as we've observed in our paper, is valuable because in the study of poroplasticity and geomechanics, it's very difficult to load a sandstone up to the point where it's about to fail but doesn't fail. And by being able to detect the imminence of that failure, it means that we are now able to do that. So that has value, has a lot of value. So a couple of applications I can think of. So in the first instance, there's embedded sensing within reservoir rocks, and that would allow us to have a real-time understanding of situation reporting, for example. How is my reservoir filling? How is my reservoir loading? What kind of stresses are occurring in the subsurface? And the second is forecasting. We can use the information that we gain from the sensor and feed that into models of that asset or underground storage, and would be able to forecast what its storage capacity could be. So there's one application. Another application is in, again, embedded sensing, for example, in the foundations of civil infrastructure. We can tell how much load something is undergoing at a given time. So that would be useful in terms of buildings, bridges, foundational structures for offshore wind turbines, for example. The future direction for this technology is really going to be about the integration with cyber-physical systems and using what is a very versatile and embedded sensor within the ground, but we're using that as the data collection point that we can then integrate with smart cyber-physical systems. I think the next 5 to 10 years are going to be very interesting in terms of our economy and how technology is going to be involved with that. Now, I've already mentioned cyber-physical systems and, the digital twinning of our assets and infrastructure within this country. I think I would like to see this sensor employed in the integrity analysis of our subsurface storage assets for liquid fuels and gases. So that would then provide the energy industry with real-time and up-to-date data on what's happening with these assets. In doing so, it streamlines operations, and in doing so, it improves our energy resilience. I think the way in which this can enhance our understanding of geomaterial dynamics is improvements in modeling. Even a 1% improvement in our understanding of the subsurface can result in millions of pounds saved in infrastructure and investment. So yeah, I think the benefits are quite clear there.